Okay, in the last class, we have started to look at isomerism, and we saw that we distinguished between constitutional isomerism and stereoisomerism, and then we have discussed the two basic forms of stereoisomerism, enantiomerism and diastereomerism. So just to briefly review this as well, so we have enantiomers when we have two stereoisomers that are mirror images to each other and cannot be superimposed, and diastereomers are just everything else. So in the following, I would like to discuss different forms of stereoisomerism and under the consideration of whether this stereoisomerism is a form of enantiomerism or a form of diastereomerism. So a very common form of stereoisomerism is the cis-trans isomerism. This occurs in organic chemistry, but it also occurs in coordination chemistry. So generally, we have a cis isomer when there are two ligands in geometrically adjacent sites, and we have a trans isomer when we have two ligands on opposite sites. So this type of isomerism is most common in square planar complexes, but it's not restricted to square planar complexes. So of the square planar complexes, platinum 2+ is most intensively studied, in part also because square planar platinum complexes are anti-cancer drugs. So in particular, cisplatinum is an anti-cancer drug. It has even this cis-trans isomerism in the name. So cisplatinum is actually cis diamine dichloro platinum, whereby the two amine ligands are in cis position and the two chloro ligands are in cis positions as well. You see the structure of the cisplatinum here. So like I just said, you see that the amine ligands are here adjacent, yeah, and the two chloro ligands are also adjacent. If we had a trans platinum complex, the structure would be this structure here. So in this structure, obviously, the two amine ligands are in opposite positions, and the two chloro ligands are in opposite positions as well. So this kind of isomer can have significant implications for the properties of the compound. So while this cisplatinum is actually an effective anti-cancer drug, the respective trans isomer is actually not. So cis-trans isomerism is not restricted to square planar complexes. It is also common for other shapes. So for example, octahedral complexes also show cis-trans isomerism. So here's just an example. So here we have an octahedral complex with two aqua ligands in trans position here. There are also a chloro, a bromo, and an oxalato ligand attached to the cobalt here. So there is a cis isomer that corresponds to this trans isomers, and in this cis isomer, the water ligands, the aqua ligands, are in adjacent position as you see here, and then the chloro and the bromo ligands, they are in opposite position. So whenever in an octahedral complex, two ligands of the same type are in cis position, they must be on the same face of the octahedron, and you can see this here. This is one face of the octahedron, and it contains this one chloro ligand and these two aqua ligands here, whereas over there, there would not be, well, the two ligands sharing a common face. All right. So now another important form of isomerism, which is actually not known to my knowledge in organic chemistry, is the FAC-MER isomerism. So FAC stands for facial, and MER stands for meridional. So now, what does that exactly mean? It means that when we have a FAC isomer, then the ligands, or the identical ligands, are on the same face of the polyhedron. And when we have a MER isomer, then the respective ligands are in a plane bisecting the respective molecule. So that is very common for octahedral complexes, but not restricted to octahedral complexes. So here is one example. So here we have a triamine trichloro cobalt complex, and one is FAC and one is MER. So this one is actually FAC and this is MER. Why is that? Because in this one, the 3 chloroligands here are on the same face of the octahedron, and these 3 amine ligands are also on the same face of the octahedron. Okay, so you see here the face number 1, and you see here the face number 2. Whereas here, the same ligands are on planes that bisect the molecule. Okay, so you see that these 3 ligands are now here on this plane that bisects the molecule, and you see that here these 3 amine ligands are also on a plane that bisects the molecule. Okay, just bisect the molecule in different, these 2 planes bisect the molecule in different ways. All right, now we can ask, are these molecules diastereomers or are they enantiomers? So in order to cite that, we would need to determine, well, are these 2 mirror images to each other or not? So can you see if they are mirror images or not? You may unmute yourself.
I think they're diastereomers.
They're diastereomers, correct. So they are not mirror images to each other, so they must be diastereomers, correct. All right. Then there are other ligands that can also do FAC-MER isomerism that is common not only for monodentate ligand, but also for tridentate ligands, for instance. So one example of a tridentate ligand is diethylene triamine, as you see here. As you have here these 3 amine groups bridged by 2 ethylene groups here and here. So in coordination chemistry, for clarity reasons, often only the donor atoms of multidentate ligands are shown that are then connected just by a band line, as it's shown here, and we will use that kind of symbolism in the future for clarity reasons. So what FAC-MER isomers could we make with this ligand? So this one here is the FAC isomer, this is the MER isomer. You see that in this isomer here, the 3 donor atoms of the same ligand are on the same face of the octahedron, and the other 3 donor atoms of the other ligand are on another face of the octahedron. So this would be the FAC isomer. So here, this is the Mer isomer, and you see now that these three donor atoms, okay, they actually lie in a plane. Okay, these are all on a plane that bisect that octahedron. Okay, so the entire plane could be thought of these 4 nitrogens here. Okay, that would bisect the octahedron. And the other 3 nitrogens would also be part of a plane that would bisect the octahedron in a different way. So the 4th atom that would be part of the plane would be, in this case, this one. Okay, and then we would have, no, I'm sorry, it's actually this one. So these 4 nitrogens here, you can see, make a plane, make a square that bisects the octahedron. Okay, and these 4 here, they make another square that bisects the octahedron. So therefore, this would be the Mer isomer. All right. Now there can be also isomerism, which is related to fragment isomerism when you have a tetradentate ligand, such as a tetraamine complex. So in this case, we have 1, 2, 3, 4 amine groups with 4 nitrogen donor atoms, and 1, 2, 3 ethylene groups that bridge the nitrogen donor atoms. So again, this ligand can be simplified as this. Ligand here, where only the nitrogen donor atoms are shown, and they are connected just by bent lines. So now, what octahedral complexes can we form with this ligand, assuming that there are 2 additional monodentate ligands that make the octahedron complete? So one possibility is to arrange all the 4 nitrogen donor atoms within a plane. Okay, so that means that you actually have 3 coplanar rings. Okay, so this is the first ring here. This is the second ring here. And this ring here is the third ring here. So you see all rings are coplanar, and the remaining ligands, in this case just generic ligands X, are in opposite positions here. Okay, so this is therefore called the trans isomer, because these 2 remaining ligands X are in opposite position. Okay, so this molecule here is not chiral. Okay, we can easily see that there are mirror planes in this molecule, and because that molecule is not chiral, we know, well, there can't be an enantiomer to it that would be its mirror image, because enantiomerism always requires chirality. So this must be therefore a non-chiral diastereomer to other possible isomers. So now, what are the other possible isomers? So one possible isomer is this one. And you see that in this one, you now only have 2 coplanar rings, namely this ring here and this one here, which are still the same as this one and that one. But now the third one is now out of plane, because that donor atom here moves into this position. Okay, so that then forces 2 remaining monodentate ligands here into these positions here. They are no longer trans, but they are now in cis position relative to each other. So now when you analyze the symmetry of this molecule. Is this molecule still non-chiral or is it chiral? You may unmute yourself.
I'm gonna guess it's achiral still.
That's actually incorrect. So if it was achiral, then there would still be rotation reflections in the molecule.
So okay, I'm thinking of it. Oh, sorry. I was just I think I just thought of it like in organic chemistry when you want a carbon atom to have all 4 different bonds to be different in order for chirality to occur. So I saw 2 of the same bond and thought of that, but I just realized that was an organic line of thinking. Sorry.
Yeah. Well, that's actually not the criterion, really, also not for organic chemistry. When you look back, when we discussed symmetry, I also showed you examples in which the carbon was surrounded by 4 different substituents, and it was still achiral. So this is actually never the real criterion, regardless whether we look at organic compounds or inorganic compounds. The real criterion is whether you have a rotation reflection in your molecule or not. If you have a rotation reflection, it's achiral. If you do not have a rotation reflection, it's chiral. Remember that rotation reflection also includes simple mirror planes, but the simple mirror plane is just an S1 rotation reflection, and inversion centers, because an inversion is the same as an S2 rotation reflection. So this molecule does not contain a mirror plane. It also doesn't contain an inversion center, and it also doesn't contain any higher order rotation reflection. No S3, S4, S5, S6, S whatever. Okay, for that reason, it is chiral. So what symmetry elements are actually in there? So the identity, certainly. Is there anything else but the identity?
No.
No, it's only the identity. So that means that the symmetry point group is actually C1, right? And that makes that molecule certainly chiral. All right, so now this is a chiral molecule. You see that, well, this molecule here is certainly not the mirror image to this molecule. Okay, so therefore these two will be diastereomers to each other. Yeah. But because this molecule is chiral, there must be an enantiomer to it, which is the mirror image of this molecule. Okay. And the mirror image of this molecule is now this molecule. Okay. So it results when you move this ring here to the other side and move this ring here to the other side, and then this X moves over there. Okay, then it's here. So that mirror image is this is the mirror image to that molecule, and they are enantiomers relative to each other. So this molecule here would be again a diastereomer relative to this molecule. Yeah. So these enantiomer forms are the so-called beta isomers having 2 coplanar rings. So now when there's a beta isomer, there must be also an alpha isomer, and that alpha isomer results when you make all rings non-coplanar, and that is actually shown here. You see now this ring here is not planar to this one, and this one is not coplanar to this one, and this one is also not coplanar to that one. Okay. Now, when you look at this molecule here and compare to that one and that one and that one, then this one is not the mirror image of any of these other 3. So this one will be a diastereomer relative to the other ones. Yeah. But when you analyze the symmetry, you see that this molecule is again a chiral molecule. Okay, so there is no mirror plane in this molecule. There is no inversion center in this molecule, and there's also no higher order inversion. Higher order reflection, rotational reflection. Okay, therefore there must be an enantiomer to this one, and this is that one, and you see that this one is just the mirror image of that one. So this ring moves from here to over here. So this ring remains the same, but this ring here moves from the right side here to the left side. Okay, so the two remaining substituents X, they remain in their position. Okay, so this is so-called alpha isomer that has no coplanar rings. Okay, so this is also a nice example that illustrates what distinguishes enantiomers from diastereomers. So another interesting aspect of these molecules, so some of these molecules are what is called propeller complexes. And we have a propeller complex whenever we have a molecule that contains rings that are not adjacent and not coplanar, because in this case, the rings stand like the blades in propellers to each other. Okay, so for instance, in this molecule here, this ring and that ring would be non-adjacent because they do not share a common nitrogen atom, but they would also not be coplanar. So you could view this ring here and this ring here as propeller blade, which is part of a two-bladed propeller. Okay. So this molecule, however, would not be considered to be a propeller complex because all the rings are being coplanar. Okay, and the propeller blades are never coplanar, because if they were coplanar, the propeller wouldn't work anymore. Okay, so now here in these molecules, you also have a propeller complex, because this ring here and that one ring here, okay, would be non-adjacent and not coplanar. Okay, so whereas this ring here, okay, would be adjacent to both this one and that one, because this ring here shares nitrogen atoms with this ring and that ring, respectively. Okay, so there's a special nomenclature for propeller complexes that I would like to discuss in the following. We distinguish between so-called left-handed propeller complexes and right-handed propeller complexes. So we define a left-handed propeller generally, that a propeller that when rotated counterclockwise moves away from you. Okay, and a right-handed propeller would then rotate, would need to be rotated clockwise to make it move away from you. So now when you have a left-handed propeller, then the tips of the propeller blades always describe left-handed helix, and when you have a right-handed propeller, the propeller blades describe a right-handed helix. Okay, and that means that we have to go clockwise along the helix when we have a right-handed propeller, and we have to go anti-clockwise along the helix when we have a left-handed propeller. So now let's go away from these general considerations to actual complexes. For instance, this one. So this is an octahedral complex with 3 oxalator ligands here. And you see immediately that the 3 rings formed between the ligands and the metal center are not coplanar and not adjacent. Okay, so this ring is not adjacent to this ring, which is not adjacent to that ring. And these 3 rings are certainly also not coplanar. You consider that this is an octahedron here. So therefore, these rings here behave like propeller blades of a 3-bladed propeller. So now, is this a left-handed propeller or is this a right-handed propeller? So if it's a left-handed propeller, it gets the designation lambda. If it's a right-handed propeller, it gets the designation delta. But how to determine whether it's lambda or delta? Now, in order to determine this, you have to first move this or rotate this molecule so that one of the rings points to the back and is horizontally oriented. So now you can choose any of the 3 rings in order to do this. So we choose arbitrarily the ring 1 here. We could also choose ring 2 or ring 3. So now the easiest way to do this is to make this ring first to be oriented, well, horizontal, and then rotate the molecule again to make it point to the back. So let's do the first step. For clarity reasons, we can actually here define a square in our octahedron. And the square would be comprised of these 2 and these 2 oxygen donor atoms, and 2 of these donor atoms would belong to the ring 1. So we orient our molecule now so that that ring here is oriented horizontally. Okay, then you see that the ring 2 would be oriented this way and the ring 3 would be oriented that way. Okay, that is because, well, if these 2 oxygens of this ring are now basically in the plane, these 2 here must be so too. Okay, so that would define the square, and then the 2 other oxygens must be above and below the square respectively. So now our ring 1 also needs to point to the back. Okay, so therefore we have to rotate this molecule in our mind now by 90 degrees clockwise. Yeah, like this. And then you have what you want. Now your ring 1 is still horizontally oriented, but it it's now pointing to the back. So now as you do the rotation, of course, you also rotate the other rings around. So now ring 3 would actually stand here. So this atom of ring 3 would still be on the original position. But this atom here of ring 3 will now be in the front. It will now be here. Okay. With regard to ring 2, as we rotate here around this axis, well, this will not affect the position of this atom, but this atom here, okay, will rotate not by 90 degrees, and then it will be here on the other side. Okay, so now our ring 3 is in that position. So now you can determine whether this complex is lambda or delta the following way. You actually draw a horizontal line in between the donor atoms, of the ring that is oriented horizontally and point to the back. And then you draw another line through two donor atoms of another ring, which is a propeller blade relative to the ring that we are looking at. So one which is not coplanar and which is not adjacent. So we could choose either this one here, ring 3, or ring 2. So in this example, we choose ring 3. So now you decide whether you have to rotate this horizontal line clockwise or counterclockwise in order to make it parallel with this line, okay, whereby you want to rotate around the smallest possible angle. Okay, so now you see that in this case, you need to rotate this horizontal line clockwise in order to make it parallel to the other line. Okay. If you rotate it counterclockwise, okay, you would have to rotate around a much larger angle to make it parallel. So therefore, we have in this case a lambda isomer. We have a lambda twist oxalator ferrate 3. Okay. So note that this molecule here is a chiral molecule, and therefore there must be an enantiomer to it. And that enantiomer would then be the left-handed propeller complex or the delta twist oxalate to ferrate 3. Okay. So now when molecules have multiple rings, then it may be that more than one delta or lambda label may be needed in order to determine the complete configuration of the respective molecule. And I want to give you an example for that as well. So in order to do this, you would first need to determine the handedness of each pair of rings which are non-coplanar and, well, not adjacent, and then include all the designation for the different ring combinations into the final description. So an example for this is this cobalt EDTA complex here. So you see here the cobalt in the center, and you see here the two nitrogen atoms of the EDTA. And you see here the additional oxygen atoms of the EDTA. Again, the ethylene units that bridge the nitrogen atoms, as well as the acetyl groups that connect the nitrogen atoms with the oxygen donor atoms, are just symbolized by these bent lines for clarity. So now we first have to analyze how many ring combinations we actually have to consider in order to account for, in order to be able to make a full determination of the handedness. So you see that overall we have 5 rings here. So this ring here is labeled R1. This one is here R2. This one is R3, this one is R4, and this one is R5. So now do we have to consider all possible ring combinations? The answer is no, because we only need to consider those which are coplanar, which are not coplanar and not adjacent. So you see that ring R3 is adjacent to all other rings. It's adjacent to R5 and R4. And it's also adjacent here to R1 and R2. It shares this nitrogen donor atom with R1 and R2, and it shares this nitrogen donor atom with R4 and R5. Therefore, we do not need to consider ring R3 at all. So what else is unnecessary to consider? You see that R5 R4 and R5 share this nitrogen donor atom, so that's also not a ring combination we need to consider. And R1 and R2 now share that nitrogen donor atom. Okay, so what's left? Well, with respect to R4, okay, you see that R4 is coplanar with ring R2, even though not adjacent. So that's also not a combination to consider. But it's not adjacent, also not coplanar with ring R1. So therefore, the R4-R1 combination is certainly a combination to consider. So what else? Well, when we look at R5, we see that R5 is not coplanar and not adjacent with ring R2 and with ring R1. Okay, so that's another combination. So another two combinations to consider. So overall, you see that we have three possible combinations to consider. Okay, so now with which combination do we start? In principle, it doesn't matter, but often the rings are already oriented to that. The combination, the identification of one combination is easier to do than the identification of another combination. So we see that in this case, the ring R4 is actually oriented correctly. You see that's oriented horizontally and it points to the back. Therefore, it's fairly straightforward to determine the R4-R1 combination. The only thing that we need to do is we draw a horizontal line through the donor atoms of ring R4, and we draw another line between the donor atoms of the ring R1. Then we decide, well, how do we need to rotate the horizontal line to make it parallel to the other line? Okay, so now I see the smallest angle around which we can rotate is actually requires us to rotate this way around. And that's counterclockwise. And that makes this ring combination a left-handed combination, which is associated with the symbol lambda. Okay. So now what about the other two ring combinations? R5, R1 and R5, R2. So now you see that it will be most convenient if we rotate R5 in a position that is oriented horizontally and points to the back, because then we can directly see the handedness of the combinations with R2 and R1 respectively. So now, in order to make it coplanar, we basically need to bring this oxygen atom into this position, because that nitrogen atom here of ring 5 is oriented correctly. And that means that we have to rotate around this square plane by 90 degrees. Okay, so basically this here, this blue line would be our axis around which we rotate. Okay, it would go through this nitrogen, this cobalt, and this oxygen. Then we rotate by 90 degrees, and then that will rotate this R5, at this oxygen of R5, into that position. Okay, now it will of course rotate also the other atoms in the square. So it will move this oxygen of ring R4 from this position into that position, and that oxygen of ring R1, oh no, sorry, yeah, this oxygen of ring R1 from this position to that position, and it will rotate this nitrogen from this position into that position. Okay. So now when you do all the reassignments and connect the rings correctly together, then our molecule looks like this. So you see that the ring R5 is now oriented horizontally and points to the back. You see that the ring R2 is now oriented this way. That is because we rotated this nitrogen here from this position into that position. Okay, so this oxygen actually stays, and then when you connect this, our ring stands here. Can you see this? So now, what about the ring R1, for instance? So you see, for the ring R1, we said that we move this oxygen here and this nitrogen over here. Therefore, our ring R1 stands now here. So what about R3? Well, this nitrogen of R3 doesn't move, but this nitrogen moves here, and therefore our R3 ring stands now here. And lastly, R4, which is here, stands now here, and that is because this nitrogen doesn't move, but this oxygen moves, well, from here to here. So therefore it's now here and connects the nitrogen, which is still at its original position. All right, so now we have done this transformation. So the rest is relatively easy. We draw a horizontal line through the donor atoms of R5. And then we look at the other rings. So for instance, the ring for the ring R1, we connect this oxygen and this nitrogen here. So now we see that we have to rotate our horizontal line clockwise. Yeah, or this way, it doesn't matter. We could either do it this way or that way, doesn't matter, but it both is clockwise. Yeah. So therefore, this combination would get a delta designation. Now, for the ring R2 here, we would connect this oxygen and that oxygen. So now how would we need to rotate this horizontal line to make it go planar? It's a parallel. And you see that in this case, you would have to rotate it counterclockwise, so that designation would be delta. So we'd have two deltas and one lambda. So that would be lambda delta, therefore lambda delta lambda ethylene diamine tetraacetyl cobaltate 3. Okay, whereby the order of this designation is arbitrary. Okay, we could have also called it delta delta lambda, yeah, or lambda lambda delta, or delta lambda lambda. Yeah, but there have to be two lambdas and one delta. But the order of these is arbitrary, because no particular ring basically deserves to be named first, second, or third, respectively. Okay, so last but not least, let's practice this a little bit together. So we see here another complex, which is on two rings, so it's a little easier. You see that they are not coplanar and also not adjacent. So can you tell me, after having rotated the molecule correctly, what is the handiness? Is it lambda or is it delta? So once you have the answer, you may unmute yourself.
Maybe this is a delta.
It's a delta. Let's see. So the easiest way to solve this problem would be to rotate this ring here by 180 degrees, because this is already oriented horizontally, but we need to make it point to the back. Yeah, then that means that R2 actually moves over there, because we would rotate this nitrogen here by 180 degrees into this position. So then we draw the horizontal line this way and the other line that way. And now, how do we have to rotate? Well, say this way, and that's clockwise, and that makes it indeed a delta. Correct. So last but not least, let's briefly look at the ring conformation. So the absolute structure is not only determined by the handedness of the propellers, also the ring conformation play a role. And again, these ring conformations can be either lambda and delta. And that is because when you have, for instance, such a ring with an ethylene diamine unit, that ring is not a planar ring because of the sp3 hybridization of the atoms. Okay. So that structure here doesn't consider the possible conformations, and there are actually two conformations possible. And again, one is lambda and one is delta. So these are the two conformations, and you see directly that these two conformations are mirror images to each other. Okay, so now which one is lambda and which one is delta? So again, you draw a horizontal line to the two donor atoms that are oriented horizontally, and then you determine, well, do you have to turn this horizontal line clockwise or counterclockwise to make it parallel to the respective carbon-carbon bond here. Okay, so now in this case, you see you need to do it counterclockwise. Okay, so this makes this delta, right? Whereas here, you need to do this clockwise. So therefore, this is the respective lambda conformer. So to indicate that this is a conformer and not an isomer, we use here lowercase letters lambda and delta, whereas previously we used capital letters. Okay, so this is all that I wanted to say about isomerism. We can now stop the recording.